Part 2 of our workshop. I made a boo-boo, so I've started all over again. Look at how humanized and approachable I've made myself. So this is part 2. Part number 2. Here we go, and do some electrochemistry. So the equation you need is delta G, the Gibbs free energy, under standard conditions, for an electrochemical cell is equal to minus the number of electrons in the process, N, and the number of electrons in process, multiplied by F. This is the Faraday constant. And if you have a spare 10 minutes, Faraday's Wikipedia page is well worth reading. Multiplied by, this is probably the weird bit, E0. This is the standard potential of the cell. And if we just talk about the maths of this for a moment, physicists measure this in terms of the number of moles of electrons. But we usually care about the number of moles of atoms because we are enlightened beings. And that's why we scale it by this factor. So this N is, if you like, the proportionality constant between atoms and electrons, because it tells you how many electrons there are per atom. So we've got some examples. This is just to make sure you are comfortable with doing the maths, so that you're ready to go when we do our frost diagrams. So our first example is a zirconium 1. We are going from zirconium 4+, and we are travelling to elemental zirconium, zirconium 0. This is a process that will require 4 electrons. You can see that to balance that charge, we need to add 4 electrons. So we should be able to do... Oh no, I've drawn on this again. Oh no. Look at that, I'm so incompetent. Oh well. Delta G, the Gibbs free energy under standard conditions, is in this case equal to minus 4, the number of electrons in the process. You're a 4, don't forget it. Because I might. Multiplied by the Faraday constant F, which I've saved in my calculator. It's about 96,000. Can that be right? That feels wrong. Maybe it's right. Multiplied by the standard potential of the cell, which is minus 1.55. Minus 1.55. So that's the thing we can now punch into our calculators. And if you forget your calculator in this exam, you really are screwed, so please don't do that. Ooh, I've got a really big number. I've done it again. Is the Faraday constant that big? It's 90,000. Can't that be right? Minus NFE0. Whew. Whew. So my raw answer here, 598,209 joules. We can make this a bit more reasonable by talking about it in kilojoules. 598-ish kilojoules. That seems super big to me. But maybe it is. We're doing a lot of stuff there. We're transferring a lot of electrons. Good practice here is to always put the sign of your delta G. So I would suggest you put a plus sign there to indicate that this is an unfavourable process. And that makes sense. So under the standard conditions, this aqueous environment, you are losing a lot of bonding when you go from zirconium 4+ 2 zirconium 0. What this is telling you is that that's a lot of bonding. Like, wow. Yeah. Let's try the next one and see if my numbers are that big. Vanadium. I've given you quite a fun example here. You're so welcome. Vanadium oxides 2+, the vanadate ion. I think you make one of these in the labs. Maybe that was even last semester. And we're turning into vanadium 2+. This oxidation state here is vanadium 4. That's not trivial. You need to work out what the oxide is doing there. There's a 2- ion. So this transition here to vanadium 2+ is going to take 2 electrons. That's what it's going to require to make those charges balance. I can shrink this and put it in the corner. Come on, come on. Nope. It's a bit sad. Nope. Oh well. Oh well. Delta G, the Gibbs free energy under standard conditions, is equal to 2 electrons, n is 2, multiplied by this suspect Faraday constant. Can it really be that big? It's so big. Multiplied by the potential of the cell, plus 0.08. So we're expecting a smaller number, but also a negative number. Let's do a calculation. Minus 2 multiplied by the Faraday constant, multiplied by 0.08. Okay, we've got minus. We've got 15437. That's in joules, so we can divide by 1,000 and make it into kilojoules per mole. And this looks a lot more reasonable. Some things to note: this is a favourable process. This reduction is favourable under standard conditions. And that looks like a much nicer number. So you would lose some bonding, no, you would gain some bonding on going to vanadium 2 in an aqueous environment, but not end of the world amounts. Last example for electrochemistry. Oh no, it's horrible. What was I thinking? We're going to have to work out this oxidation state. There's some molybdenum, there are lots of oxides, and we're going to moo. I'm going to put those oxides like that just so we can have a little fun in this our education. Should we write this one out as well? Like moo minus. Okay, I think this is molybdenum 7. I think we talked about this a little earlier in our part 1 answers. So I think this is molybdenum in the +7 oxidation state. And this mu species on the right, I think this is molybdenum 4. If that's true, then this will require 3 electrons as a process. And knowing that, we can start our calculation. Oh look, I can shrink it now. Let's put it, no, oh no. Yeah. It's the little things that make this life worth living. The Gibbs free energy under standard conditions is minus the number of electrons involved in the process, multiplied by Faraday's constant, multiplied by the standard potential of the cell. In this instance, this means we're multiplying by minus 3 electrons in the process. Faraday's constant is a constant, so we'll multiply by that again. And here the standard potential of the cell is plus 0.6 volts. I take my calculator. I plug everything in, and I get minus 173,673. That's a 3. It kind of looks like it now. That's in joules, so I can divide through by 1,000 and make this in kilojoules per mole. And now we can comment upon this. This process is favourable. Going from the +7 state to the +4 state under standard conditions is favourable. And it's quite favourable. Look at that. So a good number to have in your head is a standard strength of a covalent bond. So a CH bond will vary in bond strength in different situations, but it's usually in the region of 300 to 400 kilojoules per mole. And that's, I think, a useful thing to think about whenever you have a comparison to make. This is worth something like half of a CH bond. So that's not to be sniffed at. That's a good number. That's a good number. And I think this closes our part 1 answers for today. So a huge number for part A, which made me very uncomfortable. And if you disagree with that, come find me in the workshops and we can discuss that. But parts B and C there in question 4, I think they were all right. I felt confident there. Good. Bye for now. I'll see you at workshops.